So now I want to turn to a topic that you've probably seen defined before, but I want to drill down to where does this matter for physics? So you've seen a vector space defined. There are a bunch of rules about when you're allowed to add things and multiply by coefficients and when inverses exist and things like that, but that's not the most important thing. Let me start you off with the equation for a simple harmonic oscillator. I have two derivatives plus a coefficient times the derivatives equals 0. We call this a homogeneous linear differential equation because of two important things that happen. First off, the sum of solutions is a solution. So if I assume that each function individually solves the equation, and I add them together, I get to distribute my second derivative across both of these terms. Distribute the omega squared across both of those. And when I group my terms and factor things back out, this is just the original differential equation. That's 0. And I can do the exact same thing with the terms for g if g also solves the original differential equation. So I added these two solutions together. They still solve the equation. And if I multiply by a coefficient, and if I try to put an extra factor of, let's call it alpha in there, a coefficient times a solution is still a solution. If I have alpha times f, I just get to factor out alpha from all of this. Alpha pulls out past the derivative. And all of this is still 0. So I can add my solutions together, and I still have a solution. It's still simple harmonic oscillator behavior. And I can multiply by a coefficient. I can scale it up or shrink it down. And that's still simple harmonic oscillator behavior. So those two things put together are the important things. And these are the same rules that vectors obey back from normal 3D coordinates and things like that. These are the essential things. So if I obey these rules, if the sum of things in the group is still a thing in the group, so I'm using group loosely here, not in the math definition sense. But if the sum of things is still a thing, and if a coefficient times a thing is still a thing, we're going to call that a vector because that's actually the thing that matters most. A sum of vectors is a vector. A coefficient times a vector is still a vector. So that means that all of the linear algebra that we develop that talks about matrices and vectors and things like that, we get to apply to simple harmonic oscillators and lots of other things. That's where we're going here. So we get the idea of a linear operator. A linear operator is something like the coefficient or like the two derivatives, where it does the two things that we need it to do. a linear operator distributes and you can pull out a coefficient. So if you're a function that sends a vector to another vector, and you do those two things, you are a linear operator. And we can represent that as a matrix under most circumstances. So everything that we develop for matrices, we actually apply to lots of other things. So matrices fulfill these definitions, but a lot of other things do too. The second derivative operator, like we saw. Multiplying by coefficients fulfills that rule. Integrating from one point to another fulfills that rule. Both of these things distribute. Well, all three of these things distribute, and all three of these things let you pull out a coefficient. But you can have a non-example, which is sometimes more helpful to see than an example, about why it's worth it to find these rules in the first place. Squaring. If you have f plus g squared, you do not get to distribute that. That is not the same thing as f squared plus g squared. When you are TAing, you are inevitably going to see students do this, and you need to catch them about that. Sometimes you need to catch yourself about doing that. But squaring is out of bounds. Derivatives, integrals, all of that are in bounds. These are all things that we can apply linear algebra definitions to.